Hello friends, welcome to the tutorial on how to use SWAN, which is the single wave analysis notebook from the Chris Wilson Neurophysiology Lab. You can see right here, this is our GitHub where you can download this IPython notebook. I've already downloaded it, so let's get right into it. We're going to start by launching the notebook using our terminal window. If you're on a Windows computer, this is called command prompt. So you're going to open it and you're going to type in IPython notebook and hit enter. This is going to launch the IPython notebook interface. The next thing you want to do is to navigate to where your version of the IPython notebook is stored. Mine's in my documents in a folder called SWAN, and here it is right here, SWAN. Okay, here we go. So before we begin, I just want to show you where I've put my files so it's really clear what I'm doing. And I'm also just going to minimize this window. I'm not going to close it. So the file that I'm going to analyze today is this one right here. This is the called rat34ECG. This is included in the repository, so if you want to practice with some sample data, this is the one that I'm using. And then I also have a settings file for this particular analysis, which you can also import to use if you would like. So here we are in the notebook. The first thing we're going to do is we're going to run the initialization block. And you can do that by either pressing the play button, which is right here on top, or you can press Shift Enter. Personally, I'm a fan of hotkeys, so I'm going to be using Shift Enter. And while it's loading, we're going to wait for a print statement right in here that's going to say load successful, and that's when I know that the notebook has been initialized. We're going to give it a minute because it wants to think really hard about making sure all this stuff works. Excellent. There we go. Load successful. And we know that our notebook is ready. The next thing we're going to do is we're going to load in our file. And to do that, we're going to press, again, Shift Enter. And it wants the full file path for this data. So I know that my data is on my desktop, so I'm just going to type in where it's at. Actually, you don't need to type it in. You can actually look. You can look at the properties of your folder to get its address. So this is where mine is, right on my desktop. So I'm going to copy paste that into this bar. And the name of the file is rat34ecg.txt. Make sure you include the file type on the end of that. And when you're ready, you're going to press Enter. Next, you want to designate the location where you would like to save all of your files. So the notebook will automatically save all of your tables and settings into the place that you designate for it. It won't do that for your graphs, you have to specify, but for your tables it will. So I want my data to be saved in a folder on my desktop. So I'm going to say the same location as where it came from, and I'm going to leave that last backslash off the end of that. And then it wants the name of my sample. So the name of my sample is rat34, but for this case I'm going to just say demo. And it's going to make a folder called demo to put all of my files in, along with including demo in the handle for all the files it saves out so things don't get lost. And I'm going to press Enter, and it's going to load my data. And I know that it's loading because there's a little star right here. So while it's loading, a quick note about the format for your files. They should be tab delimited files, not comma separated. In the future, hopefully, you'll be able to choose your delimiter, but not right now. And there should be no heading in this file. So the program expects that you will give me a text file that's tab separated that is only 2 columns, where the first column is your time and the second column is your data. And it doesn't matter how long the file is, it doesn't matter what type of recording it was, as long as it's a text file, and it doesn't matter what the range of your values are, it just expects it to be time and then your data. It also anticipates that your time is in seconds, not milliseconds, so make sure that your data is converted for that if it's not saved in seconds. All right, so the data is all loaded, and I can tell because it told me how long it was, which means it's been able to look at the whole thing. So the next thing we're going to do is we're going to graph just the raw data. And this is mostly so that I can check that the data has loaded in a way that I am familiar with. It looks correct to me. So we're going to shift enter on this one. Excellent. So here's what all the plots are going to look like. And they're in matplotlib, so that's a pretty standard graphical interface. And in order to zoom in, to check to make sure my data looks right, because right now it looks sort of like a blob, I'm going to click on the pan zoom button, and with right click, I'm going to drag to zoom in on it. All right, and there we go. That looks like ECG data. That looks correct. That looks pretty normal. Excellent. So I'm happy with that, and if I want to, I can save this graph by left-clicking on the Save button, and I can navigate to my demo folder, which is where I'm going to save all of my settings and things. So I'm going to call this raw plot. I'm going to save it. All right, now that I'm done with it, I'm going to close it. You must close these graphs, otherwise you can't progress in the notebook. So the next part is transforming your data if that's something you're interested in doing. You can't skip this section entirely if you're not interested in transforming. You have to tell it when it asks for those settings that you don't want to use any of them. You can't just skip it. And your two choices here are you can either load your settings from a file, or you can enter your transformation settings yourself. I'm going to do both just to show them. So to load my settings, I'm going to shift enter on the load settings from a file box. I'm going to designate the location of that settings folder, which is right here on my desktop. So I'm going to say it's on my desktop, and it's called rat34_settings.csv. This particular file is the one that SWAN outputs from a previous setting. Right now it won't take just any file with a bunch of numbers in it for your settings. It has to be a SWAN output file. So I'm going to press enter, and it loads it in, and then it lets me see the values so that I know what I'm looking at, which is great. These look like exactly what they were. So that's one choice for you if you want to load in your data. The second choice is entering these things yourself. So I'm going to enter them to show you how it works. So I'm going to shift enter on the next one. And so the first thing it asks me is about linear fit. My data is relatively linear, and the slope is 0, so I don't need a linear fit, so I'm going to say false. Next, it wants to know if I want to use the Butterworth bandpass filter. This is a pretty handy filter if your data is particularly noisy and you know that your real data is only within a certain frequency range. My data is not particularly noisy, so I don't need to use this, so I'm going to just enter none. Next, it wants to know if I want to use the Savitsky-Golay filter. This is a really handy filter because it sort of minimizes noise while retaining your peaks, and it's going to ask you for a window size. And this window is based on data points, not necessarily time. So the bigger the window is, the more smoothed out your data is going to be, and the smaller the window, the more coarse the smoothing. I'm going to enter a value that I happen to know works for this data, which is 251 for my window size, and a polynomial of 4. So that means it's not a really strict fit, and I have a relatively small window size. The data that we're looking at, which is an ECG recording, is captured in 4K, so that's 4,000 data points per second. So a 251 data point window is pretty small. So I'm going to confirm my settings, and then I'm going to run the transformation. All right, so here's my data after it's been transformed. I can zoom in on it and see that my events are still there, but now they're really big and enhanced compared to my background, which is now pretty short. I'm really happy with that filter, so I'm going to keep it, but I'm going to save this. We're going to call this transformed plot. And then I'm going to close it. The next thing I'm going to do is specify what type of baseline I would like to use. The baseline is important for the boundary of event detection, which we call bursts. And our choices are linear or rolling. Linear is really great for a data set like this one where you have basically a linear data with a slope of 0. So it's just going to draw a straight line across. And if your data doesn't really look like that, or you can't use linear fit to make the slope 0, then rolling is probably what you want to do, and that's going to that's going to be a better fit for you. So let's demo rolling because it's probably more likely the one you want to use. So I'm going to type in rolling, and then it wants to know what my window size is. And now this time the window size is in milliseconds instead of data points. And so it wants to know how big of a window I want to do my average across. So it's just going to take the average of each window progressively along the array to do baseline detection. So let's stick with 300. That was the setting I used before, which I can tell because it's letting me know. I'm going to hit enter, shift enter to run my baseline detection. So here we go. Black is our transformed data, and blue is the rolling baseline. And you can see that this is a really good example of what I want my rolling baseline to look like. I've got, it's pretty flat and low down here where I have just baseline, and then it's a little bit higher where I've got my events, but not so tall that it's over my events. So that's pretty good. I'm happy with that. That's a really good choice for a rolling baseline in this case. So I'm going to save this. We'll say baseline. Excellent. And then right here, if we want to, we can display your settings again. There we go. There's all my settings. Now, if you're not happy with the way that any of your settings turned out, you can rerun these settings and transformation blocks as many times as you need to get your data pre-processed to look how you would like it. If you don't want to use any of these transformations up here, you have to go through the box and say none for all of them, and then run the transformation with no changes. So the next thing we want to do is go ahead and do some event detection. So here we go. This is peak detection. It's going to find where the tallest part of each of your events are. And to do that, it's going to ask for a delta value within a given range, and this range is based on your data set. So for this data set, we're going to pick something right in the middle of 0 and 0.63. So we're going to do 0.3, and then we're going to run it. So we can see each green triangle is an event, and it did a really good job of finding exactly where my events are. That's exactly it. I'm really happy. And if I was not happy with it, say it picked up, a bunch of junk down here, or it didn't get all of these guys, I would consider changing that delta value. The bigger the delta value, the harder it is for something to be a peak. So if you want to be very exclusive, only very tall things get to be peaks, you pick a large delta value. If you want a less stringent peak detection, pretty much anything over, anything that looks a little bit peaky can be a peak, and you want a small delta value. I'll save this because I like how it looks. I'm going to call this peaks. And then it prints out a summary of how many I found. So I found in this 10-minute recording 3,224 peaks. Next, we're going to do burst detection. So this is really about hunting for the boundaries of those events. The first thing it asks is for a threshold value. This threshold value is a function of that baseline that we set before. For rolling baseline, what it is an amplitude difference. So how much taller than the baseline does the time series need to be for it to be considered an event? So we'll go with something pretty conservative right now. We'll do 0.05. Then it asks for the minimum inter-event interval in seconds. So if you have two events that are really, really close together, you could probably consider them the same event, and this is the threshold for that. So if anything is less than this threshold, then they're considered the same event. We'll do 0.1 because we know that our events are relatively close together, but they're not actually the same event. And then we run the burst detection block. Ooh. Okay, here we go. We'll zoom in. Make that a little bit bigger so you can see what's happening. Okie dokie. So here we go. In black, we have our data. In blue, we have that baseline that we did before. In red, that's the threshold line, which we set using the threshold value. These little triangles right here are the beginning and the end of the event. And you can see that our inter-event value right here is a good one because these two things are not considered the same event. So that's great. It did exactly what we wanted it to do. The changing your threshold value is going to move this red line up or down in a linear fashion. So it's just going to move up or down. So if you want it to be closer to the baseline, you pick a smaller number. If you want it to be bigger than the baseline, you pick a bigger number. Pretty happy with this. So I'm going to save it. We'll say bursts. And then close it. So the next block is an optional block if you want to do burst area. I'm going to skip it for right now because burst area takes several minutes to run because it's doing integrals on each of the events. And with 3,224, it is going to take us a minute to do, so I'll skip it for now. The next thing we're going to do is save our files and settings. So this is going to save all the tables it just generated, including the summary tables which are displayed, and the settings that we use to generate these. So I'm just going to press Shift-Enter, and it told me it saved it to where I specified it before. That's great. Makes me happy. All right, now let's do some plots. One of the types of plots you can do are the Poincare plots. This will plot the successive intervals, so you can either have your peak intervals or your burst intervals. We'll just run for an example. So you can see that this Poincare sort of has an unusual shape. It's got two periods, which is pretty interesting, and you can see the ellipse inside the Poincare right there. We can save that if we want. And it'll print my SD1 and SD2 values right here, which is handy. Next, I can get a line plot sort of showing a summary of my data. Sorry about this box right here. I don't know why that decided to stay. Oops. These two graphs are linked, so you can zoom in on any portion of it to get both what the raw and analyzed data look like for a particular time interval. And again, I'm using the right mouse to zoom in on these intervals. We'll go ahead and save that. And you can see too from here that we did a pretty good job detecting each of these heartbeats, right? So these line up exactly with where the events are in the raw data. We feel pretty good about that. The only thing that's different is the amplitude measure, and that's because when we do the transformation, it becomes relative amplitude instead of absolute amplitude. But the time all lines up great, so that's fantastic. Next, what we can do is a frequency plot. And you can see here that this is frequency over time. And you can see this kind of explains whether the two periods in the Poincare. So we have a steady decrease in frequency, so that means that the heart rate is dropping, and then it kind of picks it back up at the end. The next thing you can do is a fast Fourier transform on that frequency plot to get the power spectral density. This is a pretty common thing to do for heart rate variability. In order to change your frequency bands along with your interpolation frequency, you just type right into this box. So say you don't want it to be 4 hertz, you want it to be something else, you can just type right in. We'll stick with 4 hertz for the demo though. When you're ready, you just shift enter. It'll tell you what your settings are. Then you run the block. So here's the fast Fourier transform of that frequency plot. We can save it, and it'll print the area under the curve for the different bands that we specified. When you're ready, you can just save it out right here. The last thing you can do is histogram entropy. This is another measurement that you can do, again for intervals. So you can see that this is the histogram of the interval data, which you can save, and then underneath it'll give you the histogram entropy value. When you're done, you can save them. And then that's it, you're all done. So you can either go back to the beginning and input another data set and run through this all again. But if you're done, you can kill the kernel and keep going, or kill the kernel and be done for the day. If you are using Git to do version control, which I highly recommend, you can save the notebook after each iteration for each data file and commit that so that you have a hard record of each analysis that you run. There's some optional stuff down here which I'll continue to add to. The reason that they're advanced and optional is because they rely on packages that are not standard in the Canopy distribution, and I also have a blank cell down here for if you are super advanced and you want to run your own code or play with whatever I've got. I encourage you to do so, which is the beauty of using a notebook for our analysis. So for now, let's say that I am done. I've saved my notebook. I'm pretty happy with that. And so I open my terminal window again and I say, okay, I'm done for today. I just Control-C and it asks me if I really want to shut it down, and I say Y for yes. And it says the kernel has been shut down. So I can just close these and I'm all done. Thanks for watching this tutorial. Please feel free to email us if you have any questions or concerns. Super duper email me if you find bugs or problems. I would love to know because I want to fix them. And let us know what sort of data analysis you're doing. We'd love to hear from you. Thanks. Bye.